Very good afternoon, students.
Good afternoon.
Afternoon, sir.
Good afternoon. Let us start with the discussion. So, last class we have been studying about the structural isomerism part. In that we have been discussing about the double bond equivalent. So, number of carbons plus 1 minus of number of hydrogens plus number of halogens minus number of nitrogens divided by 2. That formula you have to use. Try to solve with the degree of unsaturation. Degree of unsaturation on double bond equivalent or index of hydrogen deficiency for C4H8. Try to figure out using the same formula. C4H8 means you will be immediately getting an idea that it can be a it can be a cycloalkane, or you are going to have an alkane system, right? One is going to be the double bond equivalent. Number of carbons 4. 4 plus 1 minus of 8 hydrogens plus no halogens, no nitrogens divided by 2. So 5 minus 4, that will be 1. Degree of unsaturation is going to be 1. So 1 pi bond or 1 ring, that is a possibility. Here in benzene, C6H6. So apply the same formula again. C6H6, number of carbons is 6 plus 1, number of hydrogen 6 plus 0 minus 0 whole divided by 2. So you'll be getting what, students?
4.
Yes, you will be getting 7 minus 3, that will be 4. That means 3 pi bonds are there and 1 ring can be possible. 3 pi bonds and 1 ring. Since we know the structure, that is a possibility. 3 pi bonds and 1 ring. Naphthalene. Try to look at the naphthalene. So this is in naphthalene C10H8. C10H8. So degree of unsaturation is equals to 10 plus 1 minus of 8 plus 0 minus 0 whole divided by 2. That means 11 minus 4, you will be getting 7. So if you look carefully, 5 pi bonds are there and 2 rings are there. 5 pi bonds and 2 rings. That is the degree of unsaturation in this particular compound. And whatever the degree of unsaturation here, C3H6O. C3H6O. 3 plus 1 minus of 6 by 2. That is going to be 1. That means 1 pi bond or 1 ring that can be possible with this molecular formula C3H6O. That means this degree of unsaturation is going to give an indirect idea. If you don't know what is the molecule they have given to you, from that you can get an idea like this type of ring can be there, yes or no? This type of ring can be there, this type of structure can be there. Such idea you can generate. C2H5Cl. C2H5Cl means 2 plus 1 minus of 5 plus 1 minus 0 whole divided by 2. That is 3 minus 3, that is 0. So double bond equivalent is going to be 0. So that means you do not have any ring or any multiple bonding. No ring or no multiple bond is possible for the molecular formula C2H5Cl, and this is nothing but degree of unsaturation of this particular compound. Degree of unsaturation of this particular compound. Right. Then comes the next type of isomerism, like after your chain isomerism, position isomerism, and different cases of double bond equivalent or degree of unsaturation. You can go with the functional group isomers. So functional group isomers are those isomers where they have same molecular formula, but the difference in the functional group will be present. When 2 or more compounds having same molecular formula, but different functional groups, molecular formula is same molecular formula, but different functional groups, whenever they are present, they are said to be functional group isomers. CH3, CH2OH, alcohols and ethers. CH3, CH2OH, CH3, OCH3, alcohol and ether. They have the same molecular formula, these two compounds, C2H6O, C2H6O, and they have different functional groups, so they are called as functional group isomers. What about different other cases? What different other functional groups what you can have?
Ketone idea.
Yeah, we'll be looking at all the cases. Acetic acids, carboxylic acids, propanoic acid, and CH3, C double bond OCH3, esters. Carboxylic acids and esters, Molecular formula, same molecular formula, but difference in the functional group. So carboxylic acids and esters, they can be also called as functional group isomers. Next case, if you look at alkenes and cycloalkanes, they can also be included in the functional group isomer. CH3, CH2, C double bond to H, CH3, C double bond to H, aldehydes and ketones. They can also be called as functional group isomers. CH3CN and CH3NC, cyanides and isocyanates, they are also called as functional group isomers. CH3, CH2, CH2NH2, CH3NH, CH2, CH3, CH3N, CH3, CH3, primary amine, secondary amine, and tertiary amine, they can also be called as functional group isomers. Primary, secondary, and tertiary amines, they are also called as functional group isomers. Nitro compounds and nitrites and alcohol plus nitroso, N double bond is nitroso, OH is alcohol. So nitro, same molecular formula is there or not? C2H5NO2. Yes or no? C2H5NO2, the same molecular formula is there. For all the compounds are not check out. C2H5NO2, C2H5NO2, same molecular formula. So these are nitro compounds, nitrite, and nitroso plus alcohol. This is nitroso group N double bond O and alcohol. So these three again will be concluded, or they can be called as functional group isomers because there's a difference in the functional group, right? CH3, like alkynes and dienes. They can again be included in the functional group isomers. That means there's a difference in the type of bonding or type of functional group. It is PHCH2H, it is like alcoholic system, whereas here we have phenolic group, here we have ether. So alcohols, phenolic OH, and ethers, they can also be included in the functional group isomers. Molecular formula has to be same. That is the necessary and the preliminary condition for a set of compounds to be called as isomers. Molecular formula is same, C7H8O, but difference in the functional groups. So benzyl alcohol, O-cresol, that is phenolic group, and anisole, that is ether. So all these three are called as your functional group isomers. Everyone got it or not? Different sets
Yes.
of compounds you have seen, like acids, esters, aldehydes, ketones, alcohols, phenolic OH, anisoles. Yes or no? Cyanides, isocyanates, every different case. Nitro, nitrite, nitroso plus alcohol, alkynes and dienes, cycloalkanes and alkenes. All these categories, they come to the set of isomers called as functional group isomers. Amines and respective oximes, that is C double bond and OH, and CH3, CH2, C double bond H2, amide and oxime, they can also be called as your functional group isomers, right? Then comes the metamers. Functional group isomers means simple. Alkyl halides are functional group isomers for which compound, Kanishka? Like which compound I'm asking? If you try to change the alkyl group, which was present to the halogen, based on that, if there is a difference in the functional group in the alkyl group of alkyl halide, then we can say they are functional group isomers. Yes or no? Kanishka, CH3Cl and CH3Br, are they isomers first of all? Chlorine and bromine, they are different, no?
Yes, sir.
Yes, got it. The
Yes, sir.
molecular formula has to same. The molecular formula has to be same first point. Then only we can talk of isomerism. Metamers. Metamers means when two or more compounds having same molecular formula but different arrangement of alkyl groups around polyvalent functional group. Around a polyvalent atom or functional group, if we have two different alkyl groups on two different sites, then they are said to be metamers. So what are the polyvalent functional groups? Like ether group, thioether, secondary amine, tertiary amine, secondary amide, tertiary amide, acid anhydride, ester, ketone, all these are polyvalent group. Polyvalent means for that two arrangements can be there. Like two alkyl groups can be connected to that particular functional group or atom. Like if you take amide, NH can be connected to one alkyl group, carbon also can be connected to other. C double bond O, C double bond O, acid anhydride, both the sides we can have two connections. Like whenever we have polyvalent more than two or two, if we have such a scenario, then they are said to be polyvalent atoms or functional groups. If for that groups, if two different groups are there, two different alkyl groups on two different sides of a polyvalent atom or functional group, then they are called as metamers. Then they are called as metamers. So let us go with the example. So in metamers, functional group should be same. This is the first point you should consider. If functional group is differed, what you can say? If functional group is differed, then you can include them in the functional group isomers, not metamers. Functional group isomers are not metamers. Functional group isomers are not metamers, and in metamers, functional group should be same. Let us look at the example: CH3, CH2, CH2, OCH3, CH3, CH2, CH2, OCH3, CH3, CH2, OCH2, CH3. So one side we have propyl, other side we have methyl. In the other case, both sides we have ethyl. So on two different sides, we have two different types of alkyl groups. So they can be included in metamers. And of course, we have to check out the molecular formula. 1, 2, 3, 4, 4 carbon, C4, hydrogens, 3 plus 3, 6, and 4, 10, and 1 oxygen. Here, C4H10O, again same. So same molecular formula, but on two different sides of a polyvalent functional group or a polyvalent atom like oxygen, we have two alkyl groups. Functional group is not changed, both are ethers. Only the type of alkyl groups have changed, so that is why they are called as metamers. Okay, they are said to be metamers. 1-methoxypropane and ethoxyethane. Try to figure out this CH3 C double bond O, OCH3, and H C double bond O, OCH2 CH3. What are these, students? CH3 C double bond O, OCH3, H C double bond O, OCH2 CH3. Like we have just shifted this. Yes or no? The CH2 has been shifted. Here we have CH3 C double bond O, CH3. The CH2 has to be transferred. So C double bond O is retained or not? C double bond O is retained. That is functional group is what? Functional group is not changed. So CH3 C double bond O, CH3, HC double bond O, CH2 CH3. Functional group is not changed. Functional group is changed. Functional group didn't change, and thus metamers. If the functional groups are changed, then I have to include in the functional group isomerism. Because of shifting of CH2 to the other side, we have two different alkyl groups on two different sides. So that is why these two compounds are said to be metamers. What about here? CH3 C double bond OH, HC double bond OCH3. What are these? Again, CH2 has been transferred or not? These are metamers. Can I say these are metamers?
No, sir.
Why?
Sir, functional group isomer.
Yeah, functional group has been changed or not? CH3 C double bond OH is acid. CH3 C double bond OH is carboxylic acid. Carboxylic acid, whereas HC double bond OCH3 is ester. So they are functional group isomers. Functional group isomers. pH C double bond O, C double bond O, and you have C6H12. C6H12 C double bond O, C double bond O, C6H6. What are these? The phenyl group and cyclohexyl group, they have been changed or not? What are these called as? Functional group or metamers or chain or position?
Position isomers.
Position isomers, Kanishka says. What about others?
Identical.
Identical, right? Because although you change the position, everything is same similar. So even though you change the cyclohexyl ring and phenyl ring substitutions, so the two compounds are same, so they are just identical. And they are not going to be identical whenever I change the isotope, like carbon 14 if I place here. This is carbon 12. This is carbon 14, this is carbon 12. Then in that case, you can say they are not identical because the positions to which phenyl group and benzyl group or a phenyl group and cyclohexyl group are connected different. But here in this particular scenario, both are same. So obviously they are said to be identical in nature. Connectivity around the C double bond or OC double bond is identical. So both are identical. Write down this. How many number of different structures or structural isomers are possible with given molecular formula? C4H10 is the molecular formula. That means 1, 2, 3, 4 carbon atoms can be written in this fashion. 1, 2, 3, 4. It can also be written in this fashion. Try to solve this question, students, all of you. All of you try to figure out how many number of different isomers they are possible for this particular molecular formula.
Sir, two structural isomers.
Two structural isomers. Try to solve, all of you.
Yes, sir. 2.
Yes or no? Two structural isomers. What are those? Whatever I have written.
Yes, sir.
Yes. Adnan, we have till 4:30. Any issues?
No, sir.
All right. CH3, CH2, CH2, CH3, CH3, CH, CH3, CH3. So N-butane and isobutane. So these are the two compounds. Try to figure out here how many number of different structural isomers are possible with the given molecular formula C5H12. How many number of different structures are possible with the given molecular formula C5H12? So we can have a compound like this 1, 2, 3, 4, 5. All
Three
the 5 carbons in the
structural.
long chain.
Yes, sir. 3 structure.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Any other structures possible?
No, sir.
N-pentane, isopentane, and neopentane. If you try to look at any other structure, they are not going to be possible. So 3. How many number of different structures or structural isomers are possible with the given molecular formula C6H14? Try it out. How many number of different structures are possible with the given molecular formula? C6H14 is the molecular formula. It is nothing but your hexane. Like CnH2n plus 2, right? CnH2n plus 2. So it is nothing but your hexane. So in how many ways you can write down? So we can have all the carbons in the long chain. So this is the general way how to do it. We can have all the carbons in the long chain. First 6 carbons are there, 6 carbons are in the long chain only. Now I am reducing 1 carbon. That means I am reducing 5 carbons. So whatever other carbon we have, that I am taking as substituents. That substituent where I can place? I cannot place at this terminal positions. If I keep the substituents at this carbon or this terminal, it again becomes 6 carbon chain. So I can place at this position or I can also place at this position. Yes or no? Because two distinct positions are there, substitution can be placed at second or third. So these are two different compounds with the 5 carbon chain length. We cannot place here again because these two are symmetrical. These two are again symmetrical, so you cannot place substitution here and say they are isomers. So now 6 carbon to 5 carbon I have reduced. From the 5 carbon, I have checked out all the possibilities. From the 5 carbon, can I reduce to 4 carbon? Yes, I can reduce. And if I reduce to 4 carbon, I cannot place the substitutions at the terminals. Because if I place the substitution at the terminal, what happens? It again becomes what, students? It again becomes 5 carbon, that is which has already been counted. So you can keep two substitutions you have to keep. two substitutions you can keep on two different carbons, or two substitutions you can keep on same carbon also or not?
Yes.
Yes.
So these are distinct. These are distinct. Can I keep ethyl substituent? Ethyl.
No.
If I keep an ethyl again, it
No,
becomes 5-carbon chain. So it is
No.
matching with the 5-carbon one. So ethyl cannot be kept, and all these compounds are going to be distinct. And can I reduce to 3 carbons? 3-carbon chain I cannot produce, because ultimately I am going to give the substitution, which again becomes 4-carbon. So these are the 4 possibilities. So how many hexanes are possible? The total number of structural isomers for hexanes are 6. 5. 1, 2, 3, 4, 5. 5 hexanes, right? Yes. These are the different hexanes possible for you. Similarly, can you do for heptanes? How many heptanes are possible? Let us take an example. I just add one more slide here. Just a second. All of you try it out for heptanes. How many heptanes are there? Yeah, here we are figuring out for C7, H16, right?
Yeah.
CnH2n plus 2. Yes. So first thing, logically you have to go. If you write down random products, whatever comes to your mind, then you will not end up with all types of products which are available. You have to first go with the logic. Like 7 carbons are there in the long chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now I have reduced the carbon chain length to 6, because with 7 carbon already all are there in the single bond. So I have reduced 1 carbon. 1, 2, 3, 4, 5, 6. Now I can place substituents. Where I can place substituents? I cannot place substituent at this one or this one. So I can place a different other carbons. I can place here. That is distinct. And these two positions are symmetrical, and these two are symmetrical. So I can place at this position. I can place at this position also. These are distinct. I cannot place here and here again, because that again becomes matching. So I have to one with the 7 carbon, two isomers with the 6 carbon chain length, and 5 carbon. Now let us reduce to 5 carbon. 1, 2, 3, 4, 5. I have to keep 2 substituents. Where I have to keep the substituents? I cannot keep at terminals. Terminals are excluded. I can keep substituents at these two positions. In that case, what it becomes? 1, 2, 3, 4, 5 carbon chain only. 1, 2, 3, 4, 5. Anyway, you check out 5 carbon chain only. I can also keep substitutions like this. Are they distinct or not?
Yes.
Yes. I can also keep substitutions. Can I keep substitution like this again?
No, sir.
No, because that is already counted. So this cannot be included. But can I keep the substitution on same carbon?
Yes.
2 substitutions on the same carbon I can keep. 2 substitutions I can keep on the same carbon, but that carbon can be the 3rd carbon.
Yes.
So this is also distinct, because 1, 2, 3, 4, 5, 3, 3 dimethyl pentane, 2, 2 dimethyl pentane. These are distinct. Any other type of substitution which you can keep? Can I keep a ethyl instead of
No.
methyls? Can I keep an ethyl?
Yes,
Ethyl I can keep, but where I have to keep ethyl? Can I keep ethyl in the second position? If I keep it on second position, 1, 2, 3, 4, 5, 6 carbon chain, again we are going. So I cannot place ethyl on the second position. I obviously cannot place ethyl at the terminals, because it becomes higher chain. I cannot keep at second, means I cannot keep here or here. These two terminals are also eliminated. So only possibility for ethyl is this one. Only possibility for ethyl is 1, 2, 3, 4, 5. This is the possibility. So how many obtained?
13 structural isomers.
5 in this manner. 5 with the 1 structure with the 7 carbon, 2 structures with the 6 carbon, 5 structures with the 5 carbon. Just a second. Five structures with the 5 carbons, and now let us try to reduce the chain to further 4 carbon. 1, 2, 3, 4. If it is 4 carbon, I cannot keep a substitution here or here. I cannot keep a substitution here or here. I have to place how many more substitutions? 3 more substitutions. Where I have to place them? Where I have to place them? I can place only on these 2 carbons. And can I keep ethyl? Ethyl I can keep. If I keep ethyl, it
Ethyl.
becomes 5 carbons. Yes or no? If I keep ethyl, 1, 2, 3, 4, 5, again 5 carbon chain will be obtained. I cannot keep ethyl. Only methyls I have to place. 2 methyls I can place like this. 1 methyl I can place like this. Check out this. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Any direction you check, the parent carbon chain has only 4 carbons in the maximum number. And you have 4 carbon chain with a 2, 2, 3 trimethyl butane. So this is going to be the chain with the 4 carbon. Any other possibility in 4 carbon? So this is also same, right? So if I keep 2 substitutions on this carbon and 1 substitution on this carbon, these 2 are same. And I cannot place an ethyl substituent because the higher carbon chain I am getting. So this is going to be 1 isomer with the 4 carbon chain. So 1 plus 2 plus 5 plus 1, how much? 9 isomers. And I cannot reduce one more carbon because if I try to reduce one more carbon, anyhow I have to keep the substitution. If I keep a substitution at any carbon, it becomes 4 carbon chain. So that will be interacting. So 9 isomers are there in total for C5H16. That is 5 hexanes are available, 9 heptanes are available. Is that clear?
Yes.
Yes, sir.
Yes, sir.
So this is the way how to do it. Okay, this is the way how to reduce the carbon chain and count the number of isomers without missing out any isomer. I can write the isomer like this. I can write the 5-member chain like this. I can write randomly many isomers. But if I do so, I'll miss out some isomers. So that's why you have to reduce the chain length one by one. Then you have to include every isomers in that particular chain. Right, students? This was a previous example, right? That's why I removed that. Right. How many number of different structures or structural isomers are possible with given molecular formula C4H8? C4H8 is a molecular formula. How many number of structural isomers are possible? Try to figure it out. How many number of different structures or structural isomers are possible with given molecular formula? Molecular formula is C4H8. What is the maximum number of different structures which you can generate? So I can have 4 carbons in the long chain, 1, 2, 3, 4, and C4H8 means it belongs to which category? C4H8 means it is an alkene system.
Okay.
Alkene.
C4H8 means what is the double bond equivalent or degree of unsaturation? Degree of unsaturation is how much? 4
One.
carbons plus number of carbons plus 1 minus of number of hydrogens. How many number of hydrogens are there?
8.
8 plus 0
Yeah.
minus 0 whole divided by 2. That is 1. Degree of
One.
unsaturation 1 means what? You can have one ring or one pi bond. One pi bond. So one pi bond means alkene, one ring means cycloalkane. So you have to look at both the cases. Understood or not? Because double bond equivalent is 1. You can have one ring or one pi bond. So one ring or one pi bond means you have to look at alkene systems as well as alkane systems. Alkene means you can keep like this. I can have butane with 4 carbon atoms. In the long chain I can have. With 4 carbon atoms, I can change the position of carbon-carbon double bond. I can reduce the carbon chain length to 3 carbons. I can keep a double bond anywhere. So if I reduce the carbon chain length, the double bond can be placed between these 2 carbons or the other 2 or these 2. All these 3 are going to be same. So these are the 3 possibility in the C4H8 or not with the alkene system.
Yes, sir.
Yes, any other possibility? I have reduced the 4 carbon to
Yeah.
3 carbon and I have looked at position isomers as well, like all structural isomers. Cycloalkane also we can have. Cycloalkane 4 carbons like this. I can reduce the carbon chain to 3 carbons and I can place in methyl substituents. So what is the total number of different structural isomers possible for C4H8? 1, 2, 3, 4, 5. And acyclic are how many? Acyclic are these 3. Cyclic are 2. So in total 5 structural isomers are possible. Then you have the molecular formula C5H10. C5H10 means what is the degree of unsaturation? Degree of unsaturation number of carbons plus 1. minus of
Hmm.
number of hydrogens, no halogens and no nitrogens. So degree of unsaturation is 1. You can say one ring or one pi bond, one ring or one pi bond. So you can have one ring or one pi bond is there. Pi bond means where you can have. Pi bond means you can have this system like carbon carbon bonds you can interlink, and there is one pi bond. One pi bond can be possible or one ring can be possible. If it is a 5 carbons in the long chain, I can reduce the chain length to 4. But before reducing, in the 5 carbon, I can also have position or not. It is 1, 2.
Yes, sir.
The same 5 carbon, I can also have the position. I can also have the position. So these are the 2 isomers with the 5 carbon. And whatever the 4 carbon, I can reduce it to 4 carbon. 4 carbon I have reduced, and I placed a double bond here in the terminal. And if I place double bond here, I cannot keep substitutions where? Here or here. Like terminal carbons, I cannot keep a substitution. I can keep a substitution here. And I can also keep a substitution here. These two are distinct or not? C, carbon, 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 C double bond C, C. These two are distinct because here the position of methyl group are different. These two are also position isomers. These two are also position isomers. Any other possibility in the 4 carbon? In the 4 carbon between 1 and 2 have the substitution. I can also have the substitution between what? I can also have the substitution between 2 and 3. Yes or no? Now where can I have substitution? I cannot have substitution here. I cannot have substitution here. I cannot have substitution at these two terminals because it becomes 5 carbon again. So I can have substitution here. Can I write the molecule in this fashion with the substitution here? Are they same or distinct? Are they same or different?
Same.
Same, no. So 2 methyl butene. This is also 2 methyl butene, but these two are different. So how many are getting acyclic?
5.
5, and you can reduce to 3 carbons. Let us try to reduce to 3 carbons. In that 3 carbon, if I have a double bond here, I cannot have 2 substitutions on the same carbon because it becomes 5 carbons. So with the 3 carbons, I cannot add a possibility because double bond is already there. So only with 5 carbon and 4 carbon you can write. In the acyclic, how many are there? 1, 2, 3, 4, 5. And we can have one pi bond or one ring. One ring is also possible. So I can have cyclopentane. I can have cyclobutane with 1 methyl. I can have cyclopropane because in the cyclobutane 1 methyl can be placed on any carbon. All of them are same. In the cyclopropane, I can have 2 methyls like this. 2 methyls on the same carbon. And ethyl group can also be there. Yes or no? So how many are there, students, in total? Acyclic are 5 and cyclic are 5. Yes or no? Acyclic 5 are there and cyclic also 5 are there. So we haven't missed out anything so far. So in total you have 10 structural isomers with respect to this particular molecular formula. Right? These are the same compounds which you have been written. Can you write down this and try to figure out alcohols? Can you write down this for alcohols? How many alcohols are there?
One alcohol.
Alcohols and ethers. How many are there in total that we have to list out? Can I say this type of alcohol? Like 4 carbons are there. 1, 2, 3, 4 OH. Carbon carbon single bond only I am drawing because C4H10O. First we have to look out whether the double bond. You have to calculate the degree of unsaturation. Degree of unsaturation is number of carbons 4
0.
plus 1 minus of 10 plus 0 minus 0 whole divided by 2. So 5 minus 5, that will be 0. That means there was no pi bond, there was no ring. So that we can only connect with the carbon carbon single bond lengths. Single bonds. Carbon carbon single bonds all there and COH group. So with the 4 carbon chain, I can have OH on the first position or I can also have OH on the second position. In the 4 carbon only, I can have 2 isomers. In the 3 carbon,
Yes, sir.
if I try to reduce the chain length to 3 carbon, I can have OH at this particular position 3 carbon. With the 3 carbon, I can also have OH on the second position. These two are also distinct. With the 3 carbon, OH can be at the first position, OH can be at the second position. These two are distinct. And ethers, what I can have? Ethers, I can have CH3, like I can have 2 ethyls on both sides. CCOCC, that is an ether. We can have CCC, propyl and methyl also can have. And I can also have isopropyl and methyl. So these are the 3 possible ethers or not? So alcohols and ethers.
Yes, sir.
So these are the respective alcohols, these are the respective ethers. So like that, you have to count down the total number of structural isomers with the given molecular formula, whatever the molecular formula might be. Try to find out here, students, how many number of different structures or structural isomers are possible with the given molecular formula C4H8O. Only aldehyde and ketone they were mentioned. Only aldehyde and ketone means you have to just look at aldehydes and ketones only. That means what is the double bond equivalent first? Degree of unsaturation is 4 plus 1 minus of 8 plus 0 minus 0 whole divided by 2. That is 4 plus 1, 5 minus 4. You have one double bond. Where is the double bond? Aldehyde and ketone, C double bond O is there, right? That is the double bond. There is no carbon-carbon double bond. Aldehyde C4H8O. So 1, 2, 3, C double bond H. This is the C4H8O. This is your aldehyde. And can you have any other type of aldehyde? Aldehyde means it is a terminal C double bond H. I can have N-propyl as a substituent. Also, I can have isopropyl or not. This is also aldehyde. What about ketone? Ketone means I can have 4 carbons. I can have substitution here, or I can also have substitution here. Are they distinct or same?
Same.
Same, no, because
Same.
on the second position or first position, you have substitution. You cannot have C double bond at these terminals because that becomes aldehyde again. So how many obtained in total?
3.
3.
Okay, 3 isomers are there. That is 3 structural isomers are possible with the given molecular formula C4H8O if you try to look at only for aldehydes and ketones. How many different structures or structural isomers are possible with the given molecular formula C4H11N? Try to figure out C4H11N. And you have to look at the primary amine, secondary amine, tertiary amines. C4H11N only with only primary, secondary, and tertiary amines you have to count. First, let us go with the primary amines. Primary amines means what? Carbon-carbon bonds with NH2 group. NH2 should be there in the primary amine. I can have 4 carbons in the same chain. I can also have 4 carbons, but I can change the substitution to second position. This is also primary amine. And I can reduce the carbon chain length now because with 4 carbons I have looked at all the examples. If I reduce the carbon chain length to 3 carbons, 3 carbons means I can write like this. I can also write in this fashion. 3 carbons are there, but the position of NH2 is different now. Position of NH2 is different now. Any other possibility of primary amine? Any other possibility of primary amine? I cannot reduce to 2 carbons, right? Because I have to always keep substitutions. So these are the only primary amines possible. Secondary amines, how many are there? Secondary amine means NH group, this should be there. NH group should be there. Like it is similar to your metamerism like ethers earlier. So I can have propyl and ethyl, propyl and methyl. I can have both ethyls. I can also have isopropyl and methyl. So these are 3 possibilities with the secondary amines. What about tertiary amines? These are secondary amines. These are all primary amines. What about tertiary amines? Tertiary amines we can have possibility of what type, students? N should be connected with the 3 groups. If one is methyl, other is methyl, other should be ethyl. It is the only possibility. Yes or no? There is no other possibility where you can have tertiary amine. So primary amines are how many? 4.
4.
Secondary amines are 3.
3.
Tertiary amine is 1.
1.
So this is what we got. Find the number of possible benzoate structures. Benzoate structures means benzene should be retained. Benzene should be retained with the given molecular formula C6H4X2. X2 means two X groups. What are those X? We don't know. So two X groups. Can I place two X groups on the same carbon?
Yes.
Yes.
Yes, Dimple, that is a different possibility, right? Because they are asking about the structural isomers. So I can take primary, secondary, and tertiary amines because they are all different structural isomers. Yes or no? These are different compounds or not? Primary isomers, primary amines, secondary amine, tertiary amines are all the different case of different types of compounds. So they all have to be counted separately so that we don't miss out any single compound. So can we write a substitution like this, students? Two X
Yes.
two X atoms on the same carbon. Can you write like that? Yes or no?
Yes, sir.
Yes.
If you write like that, how many bonds are there around carbon atom? Check it out once.
We can't.
If I try to, 5 bonds are there around carbon, is that possible?
No, sir.
No,
we
sir.
cannot write two substitutions on the same carbon atom of a phenyl group because the valency is going to be 5. So we can have substitution here and here. Yes or no? 1, 2, 1, 3, and 1, 4. These are the three possibilities. So 3 isomers are going to be obtained. C4H, C6H4XY. C6H4 means again you have disubstituted benzene. So I cannot have two substitutions X and Y on the same carbon. I can have X here and Y here. Same again, X I can have here 1, 2, 1, 3 substitution. I can also have 1, 4 substitution X and Y. But if you go with the other side offering, again that becomes 1, 3 and 1, 2. So these are the three different compounds which can be given to you. C6H4XY, that is going to be a molecular formula. Find the total number of possible benzoate structures with the given molecular formula is 3. Right? Find the number of possible benzoate structures with the given molecular formula. C7H9N. Try to find out all of you. With this given molecular formula C7H9N, how many benzoate structures are possible? How many benzoate structures are possible? Anyone? Kanishka has given the answer. Very good. So if you look at the different types of possibility, students, benzoate structure means you have to maintain this ring. And they said say C7, that means one more carbon is there. So in that case, I can have CH2 NH2. Count on this. This is C6H5 plus CH2 plus NH2. How much you get? 7 carbons. 7 carbons C7. Hydrogens how many? 5 plus 2 plus 2. 9 and 1 nitrogen. C7H9N. So the molecular formula is matching. So this is one of the compound which you can have. Other compound is you can have CH2 here and NH2 here. Like 1, 2, 1, 3, 1, 4 substitutions, CH2 and NH2. Or CH3, right? CH3. Methyl substitutions.
CNH2.
And NH2 can be here.
Alabashir.
So 1, 4 substitution we can write. CH3, NH2. And any other possibility we can have? We can also have this.
NH,
Yeah, NH, CH3.
CH3.
And can we have this possibility?
No, sir.
Why?
Yes.
Yes. Yes, sir.
Yes or no? Can we have this possibility? Count down the number of carbons. 1, 2, 3, 4, 5, 6, 7. 7 carbons
Yes.
are there. Hydrogens 1, 2, 3, 4. 4 plus 2. 1, 2, 3, 4. 4 plus 2, 6. 6 plus 3, 9. Hydrogens 9 are there. Nitrogen 1 is there. This possibility is available or not? This is the
Yes.
possibility which can be accepted, but here we should not include them because they are asking about benzoate. This is a possibility if they are asking about what is the total number of compounds or structures possible with this compound. But here we should not include because they are specifically mentioned benzoate. It is not a benzoate. It has a heteroatom. But in this heteroatom also we can, if you try to link out, we can have the structures CH3, CH3. We can also have the structures CH3, CH3. Different structures are there. With respect to N, you can have CH3 and a CH3. On the same side also we can have CH3, CH3. Right, students? So these are the different possibilities which are included with the non-benzoate structures. These are non-benzoate. Benzoate means only these 5. Okay, these are the 5 benzoate structures, and whatever the structures I have written there, there are non-benzoate structures. Okay, this completes your structural isomerism part, and any other structural isomerism we have missed out? Metamers, position, chain, ring compounds are included, functional group. Any other isomerism we have, structural part?
Tautomers.
Tautomerism was going to be discussed in GOC because we have to discuss about Brett's rule. Okay, remember this tautomerism concept, whatever you have, that will be discussed in GOC. I'll write down it. Tautomerism will be discussed in GOC. So I have to, so that Brett's rule can be included. Anyone knows Brett's rule? We'll discuss all that. Okay. Brett's rule also will include, and tautomerism will discuss. So then comes stereoisomerism, students. Structural isomerism means there's a difference in structure. Stereoisomerism means there's a difference in the spatial position. So spatial position is going to be differed. So molecules having same molecular formula, same structure, but difference in the arrangement or orientation of atoms or groups in 3D space. Same molecular formula will be there, same structure will be there, but only thing is the difference in the only thing will be what? Molecules having same molecular formula, same structure, but different in the arrangement or orientation of atoms or groups in 3D space. In the 3D space, whatever the arrangement they have, that is going to be differed. They are said to be stereoisomers. Stereoisomerism is classified into 2 types. What are those? Configurational isomerism and conformational isomerism. What is configurational isomerism? Configurational isomerism can be again divided into 2 parts. What are those 2 parts?
Geometrical and optical.
Yes or no? Geometrical and optical. Geometrical and optical. In the geometrical also we can have many types. What are those? Cis-trans, EZ, SYN and I.
All.
Yes or no? In the optical activity also, we'll be discussing about rotation of plane polarized light. So all these we are going to discuss. We'll start with configurational now. So molecules having same molecular formula, same structure. Same molecular formula is there, same structure is there, but differ in the arrangement of atoms or groups in 3D space. What they differ is the differ in the arrangement of atoms or groups in the 3-dimensional space. That is nothing but your configurational. In the 3D space, if they are differing in the spatial arrangement of atoms or groups, they are said to be configurational isomers. Configurational isomers can be either geometrical or optical. So we'll start one by one now. Configurational isomers cannot be converted into each other at room temperature. This is the point. Okay, because of restricted rotation. So there is a possibility of restricted rotation in the case of geometrical isomers. So that is why one isomer and the other isomer cannot be converted. In the case of optical isomer, there is a chirality. Because of the presence of chirality, again the conversion of one isomer into the other isomer cannot be possible. Right? So we have two isomers, geometrical and optical. So we'll be discussing one by one now. So geometrical isomers means they are the stereoisomers which cannot interconvert at room temperature due to restricted rotation around a carbon-carbon double bond or around a cycloalkane system. Due to restricted rotation, the bond is not going to be rotated easily. Because of that restriction, whatever the groups present on one side, they remain on that side only, and the groups on the other side, they remain on other side only. So that is why we are seeing geometrical isomerism. That is why the different compounds obtained are said to be geometrical isomers. Is that point clear, students?
Yes, sir.
So first point is stereoisomers which cannot interconvert at room temperature due to restricted rotation. They are known as geometrical isomers. Why the rotation is restricted around carbon-carbon double bond? Why the rotation is restricted around carbon-carbon double bond? That's the first question you should ask yourself. We know this. I think we have explained the same in the chemical bonding also, if you remember. Like let us look at the carbon-carbon double bond. This particular terminal is one carbon and the other terminal is other carbon. Carbon-carbon double bond means the bond, it is the carbon-carbon double bond. This carbon is having hybridization of sp2. The sp2 hybrid orbital, what is the shape of sp2 hybrid orbital? It has 66.66% p character. So it looks more like a p orbital. So it looks more like a p orbital. The p orbitals, they are going to be overlapped. This carbon-carbon sigma bond, whatever it is formed, that is formed by overlapping of sp2 hybrid orbital of one carbon with the sp2 hybrid orbital of another carbon. The carbon hydrogen bond, that is formed by the CH bond, they are formed by what type of overlapping?
Atomic.
sp2 hybrid orbital of carbon overlap with the 1s atomic orbital of hydrogen. sp2 hybrid orbital of carbon overlap with the 1s atomic orbital of hydrogen. This is nothing but a CH bond. The same scenario is present in the other case as well. The same scenario is present in the other case as well. This is all the overlapping. So CH bonds are due to overlapping of sp2 hybrid orbital of carbon with the 1s atomic orbital of hydrogen. CC single bond, that is sigma bond, is formed by overlapping of sp2 hybrid orbital of one carbon with the sp2 hybrid orbital of another carbon. But we do have one more p orbital on each carbon. We do have one more p orbital on each carbon which overlaps sidewise to actually form pi bond. The pi bond is formed by p pi bonding, that is the p orbital of one carbon overlaps with the p orbital of other carbon, forming the pi bond. Understand this carefully. If this is a carbon-carbon sigma bond, you can see this marker. The sigma bond is formed by sp2 hybrid orbital of one carbon with the sp2 hybrid orbital of another carbon. You can look like this. So here along this particular marker, you have a carbon-carbon single bond and you have p orbitals like this. My fingers, you can say the p orbitals are like this on each carbon, these p orbitals. Those p orbitals are overlapped sidewise. So the p orbitals are overlapped sidewise. So if I want to rotate this carbon, with respect to other carbon, now you can see rotator system. I have a rod which can be rotating about this axis. Yes or no? Moment of inertia also will calculate. Rotation of this carbon, if you try to look at, this carbon can be rotating with respect to the other carbon. Sorry. This carbon can be rotating with respect to the other carbon atom. Let us say here we have an angular velocity omega 1, here we have an angular velocity of omega 2. Omega 1 and omega 2, they are not equal. That means one carbon is rotating with respect to the other carbon. So one carbon's angular velocity is different when compared to the other carbon's angular velocity. Angular acceleration we're not considering about, just velocities. So I can say with respect to this carbon, if this carbon is rotating, like with respect to this carbon atom, if this is rotating, is there any disturbance in the carbon-carbon sigma bond? I can easily rotate. No, not an issue. I can rotate this particular carbon atom and I am not going to break this carbon-carbon sigma bond. But if I try to rotate the same carbon-carbon double bond, if I want to rotate this particular carbon atom, I have to break this pi bond interaction. The pi bond has to be broken to rotate one carbon with respect to the other carbon. Breaking of bond requires energy. That is why whenever we have a carbon-carbon double bond, the double bond will not be broken by itself, but it requires energy. That means if I supply energy, then only that pi bond can be broken, not by itself. So restricted rotation means the rotation is not possible around a carbon-carbon double bond because of the presence of a pi bond, which is not allowing the carbon to rotate. If it wants to rotate, the pi orbital overlapping has to be disturbed, but that overlapping is already there. So if I provide energy to break that overlapping, then only rotation is possible. If not, rotation will not happen. So what happens is, whenever I have a carbon-carbon double bond system, the group present CH3 here and H here and CH3 here. This CH3 lies here only. This CH3 lies here only because rotation around this carbon atom is not happening. If I write a carbon-carbon single bond, if I write carbon-carbon single bond, if I write carbon-carbon single bond and write methyl here and methyl here, two hydrogens in this fashion, two hydrogens in this fashion, can I say it has cis-trans isomerism? Carbon-carbon single bond.
No.
I cannot say like
No,
this
sir.
here because the rotation is possible. Rotation is possible. Free rotation possible. Here we have restricted rotation. Restricted rotation. Restricted rotation is there in the double bonded system, also in the pi bonded systems, right? So free rotation is possible. So cannot show geometrical isomerism. Which one? Whenever we have carbon-carbon single bond, rotation is free. The spatial positions are continuously changing. So obviously it is not showing any cis-trans isomerism. Whenever we have a carbon-carbon double bond, so the p bond, the pi bonding, whatever it is there, because of that rotation is not happening. Because of that rotation is not happening. Free rotation is not possible. Restricted rotating system. So can show geometrical. Cis isomer means what? Cis isomer means the two same groups. The
On the
groups
same
should be
side.
present on same sides. If the groups are on the opposite side, that is trans. If one isomer is rotated into other, it can happen only with the external supply of energy, not by itself. If this rotation is happening, then there is no cis and trans. Cis and trans has no meaning. Not only in the alkene system, we can also have cycloalkanes. In the cycloalkanes also, free rotation is not accepted. We'll discuss that as well. Restricted rotating systems are along pi bond in acyclic molecules. In cycloalkanes, along single bond. Rotation is not accepted. Geometrical isomerism condition for pi bond in acyclic molecules is, what is that? Understand this condition. Each sp2 hybridized carbon individually must have different atoms or groups attached to it. Like this is what they're saying. This is sp2 carbon. This is sp2 carbon. To this, whatever the groups you are going to have, they should be different. That is the only condition. If to this carbon, if X and Y are connected, to the other carbon, if P and Q are connected, it will show geometrical isomerism. If to the same carbon, if both the same groups are connected, it will not show no cis-trans, no geometrical isomerism. Why? Because in the same compound, if you change the positions of X and P and Q also, these two compounds are again same. These two compounds are again same. So each sp2 hybridized atom individually must have different atoms or groups attached to it. The atoms or groups attached to each sp2 hybridized carbon should be different, right? It is nothing but cis-butene. So two methyls are on the same side, cis-butene. Two methyls are on the opposite side, trans-2-butene. Cis-2-butene and trans-2-butene. This is an example. So you can look at the animation, carbon-carbon double bond, two methyls on the same side, two methyls on the opposite side. Rotation of or conversion of cis butene to trans-butene is not happening directly. Next, restricted rotating systems. Geometrical isomerism condition for cyclic molecules. There must be at least two sp3 hybridized atoms constituting the ring, and individually must have different atoms or groups attached to it. What is this? For cyclic molecules, what we are talking about? So these systems. What is the system? So cyclopropane, if you consider, there must be at least two sp3 hybridized atoms constituting the ring, and individually must have different atoms or groups. This is sp3, this is sp3. Like if I have both the hydrogens here, one hydrogen above, other hydrogen below. Both hydrogens here, one hydrogen above, other hydrogen below. So if two same atoms are present on the same, two same atoms are present on different sides, then it will not show geometrical isomerism. There must be at least two sp3 hybridized atoms constituting the ring, and individually must have different atoms or groups attached to it. Like this. This is sp3. This is sp3. And hydrogen and chlorine are connected to the same atom. We should not have same groups. Like if we have this system, if we have a system like this, for one atom we have hydrogen and chlorine connected. For the other atom we have both are hydrogen atoms. So this is one compound, and next compound is this one. Are they different or same? These two are same, no, because to this particular carbon atom, above and below are hydrogens. So if I have a 3-member ring, like I have a paper like this, just a second. Yes or no? I can have a paper like this, 3-member ring, hydrogen above, hydrogen below, chlorine above, hydrogen below. Now I am looking at the molecule from the top. For me, chlorine is above, this hydrogen above, hydrogen below, hydrogen below. For a person looking from bottom, if I change the position also, like if I change the position of chlorine and hydrogen, it becomes the same or not? Like chlorine will come above, like both the hydrogens are on one side, and if you try to change the position of chlorine also, the molecule looks the same. The molecule looks the same. If I try to change the position of hydrogen and chlorine also, for the just the position from which you are viewing, that is different. Understand this or not? If we have both hydrogens above, one hydrogen above and other hydrogen below, chlorine above, hydrogen below. Now I am changing the positions. I am changing chlorine below and hydrogen above. So if I am looking from the top, earlier chlorine and hydrogen are my sides. After I change, chlorine and hydrogen again on my side, but I am looking from the bottom. Yes or no? The molecules are going to be same. Right, students? So these two, whenever we have two different atoms on two sp3 hybridized atoms in the ring, then they will be showing the cis trans, and these are not rotatable. Which of the following compounds show geometrical isomerism? Answer this question. First, you should know whether the compound will show geometrical isomerism or not. CH3, CH2, CH2, CH double bond, CH, CH3.
Yes.
Yes or no? Because if you have,
Yes.
you look at the carbon, this hydrogen, hydrogen methyl different, hydrogen, this is what? Propyl, they are different.
Mobile.
So different means obviously it will show geometrical isomerism. It will show. What about second compound? CH3 and Cl different.
Yes.
H and CH3 they are also different. So it will also show geometrical. Here,
No, sir. No, sir.
No. Sir.
or no? It cannot show because to this particular terminal we have two hydrogens connected.
Hydrogen.
So two same hydrogens, so that cannot be showing the geometrical isomerism. Which of the following compounds show geometrical isomerism? This one will show or not?
No, sir.
No or yes?
Yes, sir.
Yes, sir.
So hydrogen chlorine, hydrogen, chlorine, and you can have on the compound hydrogen, chlorine, chlorine, hydrogen. So that is a possibility. This compound will show or not? Like bromine, we can have above, hydrogen below.
Yes, sir.
Bromine above, hydrogen below. Chlorine above, hydrogen below. Let us change one position now. Is it different or same? Bromine above, hydrogen below. Chlorine above, hydrogen below. Hydrogen above, bromine below. So the molecules are different.
Yes, sir.
So that will also show. So whenever we have three different atoms, three atoms of cyclic ring having two different atoms shows geometrical isomerism. So that will show geometrical isomerism because these two compounds are going to be different in each other in their spatial positions. Right? Try to answer which of the following compounds show geometrical isomerism. Will this compound show?
No, sir.
Why?
CH3 on same code.
So all are sp2 hybridized, but if you look at the carbon atom, both CH3s are same. So if I try to change the position of these two CH3 and H, they are not going to be different compounds. So this will not show. What about this compound?
Sure, sir.
Yes or no? It will show. PHH, HPH, because on at least two sp3 hybridized carbon atom should have two different groups. Two different groups or atoms should be present on at least two sp3 hybridized atoms in the cyclohexane or cycloalkane, then only that will show geometrical isomerism. Cis-trans system, students. Cis means what? When two similar groups or atoms are present on same side of double bond, then we name it as cis, otherwise it is trans. Like cis 2-butene and trans 2-butene, that's a very simple example. We can also say cis but2ene 1,4-dioic acid. This is nothing but maleic acid. And trans but2ene 1,4-dioic acid, that is nothing but fumaric acid. 1, 2, 3, 4. 1, 2, 3, 4. So 1,4-dioic acid, butene. So whenever you have the name of this COH, CH2, CH2, COH, what is the name of this compound? What is the name of this compound? COH, CH double bond CH. COH, CH double bond CH, COH. What is the name of this compound? 1, 2, 3, 4. 1, 2, 3, 4. Fatima, whatever the names you are saying, they are common names. Oh my, such good apples in that. Oxalic, maleic, yes or no? All those,
Yes.
they are common names. What is the IUPAC name I'm asking? But 1, 2, 3, 4
Butane
carbon atoms are there.
1,2-diene.
Butane, but 1, 1 in or 2 in?
2-ene.
2
In
in 1, 4
1,
Dioic
dioic acid.
Does this name will give the complete idea about your structure? That is a question you should ask yourself. I have given a name. You know how to name a compound. That is very interesting. You know how to name a compound. I have given the name. If I given the name to a compound, that name will signify only the type of bonding present, the type of functional group present, the position where the substituents are present. Whatever the IUPAC name you are written till now, they only try to give about the structural positions of the substituents and the structure on the structure of the molecule. They did not say anything about the spatial positions of spatial groups. If I write a but2ene 1,4-dioic acid, it can be in the cis form or trans form. Whether it is cis or trans, that is not known to you. Are you understanding that point? So if I mention cis only, if I mention cis, then you will get an idea. Yes, it is a carbon-carbon double bond system, and you have two COH groups on the same side. Whenever I write cis here, that includes the complete name, including the spatial positions, not only the structure. But2ene 1,4-dioic acid is just the structural name, like what type of structure is there, that particular name. If I include cis, then that will be giving the idea about the spatial positions also. So it will be it is also IUPAC name. It will be giving even more data about the spatial positions. Sir, you may ask a question. Sir, here in cis trans, you are saying cis and trans can be given. But if you have given an optically active compound, then how to give the spatial position names? Then we have a system known as RS nomenclature. You know RS? RS configurations? Anyone know or not?
Yes.
RS, assigning R configuration or S configuration, we will assign those at the chiral carbons. Then you will get an idea whether you have chirality or not. Whether you have chirality or not. Okay. So then comes the cis and trans means on the same side, you should have same groups. EZ isomerism, it is going to be used whenever the groups are different. E means antigen, Z means Zusamen. When high priority groups are on opposite side of double bond, it is said to be similar to trans. When high priority groups on same side of double bond, similar to cis. Okay. Similar to cis, Z is similar to cis, E is similar to trans. What's the difference? What is the difference you have? Earlier you have two same groups on same side, like butene, but2ene. If you try to mention, if you have two methyls on the same side, what do you say? Cis but2ene. You are using cis here. Why? Because two methyls are same. But now the groups connected to this carbon are different. The groups connected to this carbon are different. Then you have to give the priority. Low priority and high priority you have to assign. If a high priority groups are on the opposite side, then it is E. If low priority groups are on the same side or high priority groups on the same side, then they are said to be Z. Yes or no? Z means cis, E means trans. Cis means high priority group will be present on the same side, similar to cis. Similarly, high priority, low priority will also be present on same side. E means high priority and low priority, they will be on opposite sides. So E will be giving trans, Z will be
Trans.
giving cis idea. But everything is fine, sir. But how to give priority? You are saying high priority, low priority, but on what basis we have to give the priority? That is given based on CIP rules. What are CIP rules? Khan-Ingold Prelog rules. Yes. Based on the CIP rules, you have to give the priority order. If the same high priority groups on the same side, then you assign cis similar to Z. Yes or no? If they are on the opposite
Yes,
side,
sir.
you assign E, that is similar to trans. So rule 1, what is this rule says? The atom with the greatest atomic number has the highest priority. The atom which has greatest atomic number, that will have the highest priority. Example, we have carbon-carbon double bond. This carbon connected to iodine bromine, the other carbon connected to fluorine chlorine. Assign them. High priority, low priority, assign them.
Iodine
Highest?
high
Highest
priority.
priority iodine.
Iodine, bromine,
Yes,
chlorine,
iodine will be given the highest priority, then
bromine,
Bromine.
bromine, low priority.
chlorine,
Fluorine and chlorine, high priority will be for chlorine, low priority will be for fluorine. So what is it?
Z.
Z.
So what is the name of this compound? Name of this compound is 1,2-ethene. Yes or no? Ethene. Positions, how to name? What is the name of this compound? I have to give numbering in which fashion? When the positions are same, this first position, the second position, I can have lowest locant rule like this: 1, 1, 2, 2. If I give numbering in this fashion also, again I am getting 1, 1, 2, 2. If the lowest locant rule is same set of locants, same set of
Alphabetical order.
locants, alphabetical order. Very good. So I have to give alphabetical order. Bromine gives B, so that should be alphabetical order. So you have to give numbering in this fashion. So 1 bromo,
1 bromo, 2 chloro,
2 fluoro.
2
2
chloro.
chloro,
1 iod,
1 iodo. 1
2
iodo.
fluoro, 1 iodo,
2 fluoro 1 iodo.
2 fluoro, 1 iodo,
2 fluoro,
1 iodo,
1 iodo.
1
1
iodo,
iodo.
ethene. This will be giving name about the structure. 1 bromo, 2 chloro, 2 fluoro, 1 iodo, ethene. This is the name of this particular molecule, which gives only information regarding the type of bonding, type of linkages, where are they present. But if I write a Z here, it is Z or E. Same
Z.
high priority on the same side, Z. So Z if I mention, then you will get the complete name. Z of 1 bromo, 2 chloro, 2 fluoro, 1 iodo, this will give the complete name of this particular molecule, which is including the information regarding spatial positions also. Okay. So that's the first priority, first rule. Atom with higher or greater atomic number has highest priority. Rule number 2, if two substituent atoms have same atomic number or isotope, then the higher atomic mass will be given higher priority. Example, carbon-carbon double bond, hydrogen deuterium is there, and methyl fluorine is there. Carbon and fluorine, which has high priority?
Fluorine.
Fluorine high priority, carbon low priority. Deuterium and hydrogen, hydrogen will be high priority, deuterium will be high priority, hydrogen will be low priority based on atomic mass.
Yeah.
So it will be E. It
E.
will be E. If directly attached atoms on sp2 hybrid are same, then check the atomic number of neighboring atoms until first difference is found. What is this? We have this compound, let us say C double bond C, CH3, CH2, I. Look at this particular carbon. To this particular sp2 hybridized carbon, we have carbon connected. To this carbon, what are the three groups connected again? Hydrogen, hydrogen, iodine.
hydrogen,
To this
iodine.
carbon, we have hydrogen,
Three
hydrogen,
Hydrogen,
hydrogen.
hydrogen, hydrogen.
So this will be high priority. This will be low priority. To this particular carbon, we have hydrogen, hydrogen, carbon. To this particular carbon, we have carbon, hydrogen, hydrogen. Can we distinguish here itself?
No, sir.
No, because
sir.
CHH, CHH same. So we have to go with the next carbon. So if you go with the next carbon is connected with carbon, carbon, hydrogen.
Carbon, hydrogen, carbon,
Here,
hydrogen.
carbon, hydrogen, hydrogen. Which is high priority then?
Carbon, carbon,
High
hydrogen.
priority, low priority. So what is a cis or trans?
Cis.
Z.
Cis.
Cis.
Yes or no? Two high priority groups on the same side, so that will be Z. Z means cis. Understood now? Rule 4. If a multiple bond group is present, it will be converted into single bond by hypothetical system given by CIP. So what is that hypothetical system? We have CH double bond CH2. CH double bond CH2. Then you have to imagine, to this particular carbon, we have carbon double bond carbon. That means two same groups are connected. You have to imagine like that. To this particular carbon, this carbon is connected with the other carbon with a double bond. So we have to include two such carbons are connected. So this is one carbon, one more carbon is there. This carbon has double bond. So along with CH2, we have one more carbon. Like that, you have to convert. CH double bond CH2 is CHC, CH2C. The double bond has to be converted into single bonds by treating two such groups have been connected. CH double bond O, how we have to connect this? CH double bond O. Carbon is connected with doubly bond with oxygen. That means one more oxygen is there here. You have to imagine like this. Oxygen is connected with doubly bond with carbon. That means one more carbon is there here. So this is the imagine. That is how we have to consider the molecules whenever we have multiple bonds. How to take this case? C double bond OH. C double bond OH. C double bond OH means double bond O I have to convert to
Connected with
oxygen. Oxygen. OH is as it is.
Oxygen connected with carbon.
Oxygen connected with carbon. Right? So this is the hypothetical system. We all know that in reality such connections are not there, but we have to give this type of connectivity to figure out high priority and low priority for based on CIP rules. C triple bond N, how to give the connection? C triple bond N means carbon connected to nitrogen. So triple bond is there, so two more nitrogens it should be connected. Nitrogen connected to carbon, so two more carbons it should be connected. So now we can actually give all the high priority and low priority assignments. So try to give the assignment here. Give EZ configuration to the following molecules. To this molecule, give the EZ configuration. To this molecule, give the EZ configuration. So I can write this molecule in this fashion. C double bond C, C double bond OH, how we can treat? COH,
C double.
O, C double bond, how you can write? CO, CO, OC. C triple bond, and how I can write? C, N, N, N,
N,
C,
C,
C.
C.
Yes, right. C double bond to Cl, C, Cl, O, OC, CH2, CSH, CH2, SH. Now look at this side, CH2. What are the immediately connected carbon is same. To this particular carbon, the immediately connected atom is same. To that carbon atom, what are the other groups connected? Hydrogen, hydrogen, sulfur. To this carbon, what are the other groups connected? Fluorine,
Fluorine,
oxygen, oxygen.
oxygen, oxygen,
So it should be given the highest priority atomic number.
fluorine.
Fluorine, this should be given the highest priority, right? So this should be the highest priority. This should be lowest priority. Then to the other side, both are carbons directly connected, but what are the other groups? To this particular carbon, we have oxygen, oxygen, oxygen connected. To this particular carbon, we have nitrogen, nitrogen, nitrogen connected. So oxygen should be highest priority. So this is high priority. This is low priority. High priority groups on the same side. What is it called as?
Z.
Z.
Z configuration. Yes or no? It will be Z configuration because high priority groups are on the same side. Can you do this molecule in the same way? If you try to do this molecule, C double bond system, here we have carbons, all first atoms are same. So you have to, based on second atoms only, you have to decide. It is connected with oxygen, hydrogen, hydrogen. It is also connected with oxygen, hydrogen, hydrogen. I cannot decide on the first rule itself. If you go with the second, oxygen is again connected with CH3 here. Oxygen is connected with hydrogen here. So this will be given the highest priority. And CH, CH3, CH3, carbon, carbon, hydrogen, carbon, hydrogen, hydrogen. So this highest priority. So it will be E,
Carbon, carbon, hydrogen.
right? It will be E. What about this case? E or Z? Try to answer this fastly. E or Z? C double bond C, CHO, CH2OH, CH double bond CH2, CH, CH taken twice. No one.
E.
E means trans, you are saying.
Trans.
See, look at the case. So we have this particular molecule, C double bond C, C double bond O. You have to consider C double bond C, C double bond H, right? C double bond H means you have to treat as CO, CO, and this O should be connected to C, and this carbon is connected to hydrogen. This is how you have to consider C double bond H. And above you have to consider CH2H means C connected to two hydrogens and OH. This side CH, CH3 taken twice. This side you have C double bond CH2 means CH, C, C, H2, C. Now look at the connections. Here we have what? To the immediately connected atom is same carbon. The next atoms are oxygen, oxygen, and carbon. Oxygen, oxygen, and hydrogen, not carbon. Oxygen, oxygen, and hydrogen. Here we have hydrogen, hydrogen, and oxygen. So which should
Hydrogen,
be highest
hydrogen.
priority? So this should be high priority. To this side, what do we have? To this side, what do we have? Immediately connected carbon is having carbon, carbon, hydrogen.
Carbon, carbon, hydrogen.
Carbon, carbon, hydrogen. Here also carbon, carbon, hydrogen. Carbon, carbon, hydrogen. To next carbon, what do we have, students?
Hydrogen,
Hydrogen,
hydrogen.
hydrogen, carbon.
Hydrogen, hydrogen, carbon.
Hydrogen,
To next
hydrogen.
carbon here, hydrogen,
Hydrogen,
hydrogen, hydrogen.
Hydrogen, hydrogen.
So which should be given the highest priority?
Carbon.
This one, high priority. So both high priority on the same side. Both high priority on the same side means Z. Okay, you have to be careful while answering this. If first atom is same and the three groups connected to the first atom is also same, then you have to go with the second atom and look at the three groups connected to the second atom also. Right? So then comes syn and anti systems. Geometrical isomerism in oximes, C double bond N systems. So oximes show geometrical isomerism due to restricted rotation around double bond. Around double bond, there is a restricted rotation. Because of that, oximes show geometrical isomerism. Only those oximes show geometrical isomerism in which sp2 carbon has two different groups, like C double bond N, and this is your sp2 hybridized carbon. If it has two same groups, X and X, then there is no possibility of geometrical isomerism. X and Y should be there. Two different groups should be connected to sp2 hybridized carbon. Syn anti-system, benzoyl oximes has two isomers, geometrical isomers. Like nitrogen has lone pair of electron and carbon has hydrogen and pH groups. C double bond N, NOH. When hydrogen and OH are on the same side means syn. After cis trans and Ez, we have to go with the syn and anti. When hydrogen and OH are on the same side, it is said to be syn. When hydrogen and OH are on the same side, it is said to be syn. Hydrogen and OH on the opposite side means it is going to be anti. Understood or not? When hydrogen and OH are on the opposite side, it is said to be anti. If it is on the same side, it is said to be syn. Is everything clear, students, regarding geometrical isomerism?
Yes.
Yes, sir.
Yes, right. So we look at the few other properties like dipole moment, solubility, and all. Dipole moment arises due to difference in electronegativity and shape of molecule. Difference in electronegativity difference should be there. Then only we have a dipole moment vector, and that is also based on shapes of molecule. Like we take an example, butene, C double bond C, CH3, CH3, HH. So it is having a dipole moment vector. Why? Because the carbon, the two carbon atoms, although they are same, but they are differing in the hybridization and thus differ in the electronegativity. It is sp2 hybridized carbon. This is sp3 hybridized carbon. So sp2 hybridized carbon is more electronegative. So electron density will be moving in this fashion. Electron density will also move in this fashion. So net dipole vector will be in this fashion. This is a mu net, not equal to 0. If you take the cis position, it is not equal to 0. If you take the trans, you have carbon-carbon double bond, CH3 in this fashion, CH3 in this fashion, CH and CH. So you have one dipole vector in this fashion and the other dipole vector in this fashion. So mu net is exactly going to be 0. So mu net is not equal to 0 in the case of cis-2 butene. Mu net is exactly 0 in the case of trans to butene. Yes or no? So cis-2 butene we have net dipole moment. That means it has a dipole-dipole force of attractions. Dipole-dipole force of attractions are there. Force of attractions and thus higher boiling point. And thus higher boiling point. Here we don't have any dipole moment. So mu is equal to 0 net dipole moment. So obviously no dipole-dipole force of attractions. What do we have instead? No dipole-dipole force of attractions. We do have van der Waals forces. Instantaneous dipoles can be present. So with that, they will be having lesser boiling point. Right? 1-chloropropene. This is a scenario. You cannot say always like trans is having net dipole moment is 0. Trans will have net dipole moment 0 when the two groups are same, like both are electron donating or both are electron withdrawing. If one is electron donating, other is electron withdrawing, then we have different case. Like 1-chloropropene and like cis form of 1-chloropropene and a trans form of 1-chloropropene. If you look that C double bond C, Cl, CH3H, CH, it is cis form. Chlorine is electron withdrawing. You have a dipole vector in this fashion now. Direction has been changed. One more vector in this fashion. Look at the other way. Transform. Transform means chlorine in this fashion. Methyl will be in this fashion. So you have both vectors in the same direction. So what is the net dipole vector? Mu net is equals to under root of mu1 square plus mu2 square plus 2 mu1 mu2 cos theta sin theta.
Cos theta.
Cos theta. So whenever theta whenever theta is equal to 0, so what is the maximum net dipole moment? Mu net
Mu
of
1 plus
maximum
mu
will be mu1 plus mu2. That means this is going to the scenario when theta is equal to 0. Yes or no? So here you will be having how much, students? Here you will be having, in the transform you have greater dipole moment. Here you can write a mu net of trans is greater when compared to mu net of cis. So boiling point of trans is greater when compared to boiling point of cis. The boiling point you have to compare just based on dipole moment values. Greater the dipole moment value, dipole vector, greater will be the intermolecular force of attraction, greater will be the boiling point. Everyone got it or not?
Yes.
Do you require some 5 minutes of break? All of you?
Yes, sir.
No, right? Can I continue like this or you require? Whoever is required, just you can just type S in the comment section. No, right? Okay, fine. Then comes the solubility. Solubility, how we can compare? Solubility means we have discussed about like dissolves in like. Like dissolves in like. Like dissolves in like means what? Like polar solute dissolves in polar solvent. Non-polar solute dissolves in non-polar solvent. That means whenever we have a particular substance which is polar in nature, it is added to some other substance which is also polar. The interactions between two polar substances will be developed. Because of that, what happens? Because of that, the new interactions are going to be stronger and that will be soluble in nature. If we have one substance which is polar, other is non-polar, then when you add them, the new interactions are not going to be stronger and that will not be produced greatly. So solubility means if a molecule is polar, it will be soluble in polar solvent like water, alcohol, etc. Like dissolves in like. If a molecule is non-polar, it will be soluble in non-polar solvents like benzene, hexane, CCl4, CS2, etc. Non-polar solutes or non-polar molecules will be soluble in non-polar solvents like benzene, hexane, CCl4, CS2. Cis molecule is generally less stable than trans molecule. As in cis molecule, there is repulsion between the groups present on same side. Obviously, right? Cis molecule means the two groups are on the same side, so they are going to be having repulsions. Steric repulsions will be there in the cis molecule. Because of that repulsions, the cis molecules are going to be unstable or less stable when compared to trans molecules. So more repulsion will be there in the cis molecule and less repulsion will be there in the trans molecule. So we have looked at boiling point, we have looked at solubilities, and then we can also interact with the melting point, which will have higher melting point. Among cis and trans, the boiling point, if you want to compare, what you will compare? If you want to compare boiling point, you will look at intermolecular force of attractions. If you want to compare melting point, what you are going to look at? You have to look at the packing efficiency, which can be packing greatly. Like melting point means now the compound is in the solid state. It has to convert into the liquid state. Solid to liquid means melting has to happen. So in the solid, it has a crystal lattice structure. So in that crystal lattice structure, it has different packing efficiencies. Greater the packing efficiency, greater the density. So which has more packing efficiency? Look at the structures. If you take the cis molecule and the trans molecule, where the packing efficiency is more?
Trans.
Trans.
Trans molecule has higher melting point than cis molecule, as trans molecule is more symmetrical and shows high packing efficiency compared to cis. Why? Because in the cis molecule, whatever the space left here, that is all empty. That is all void space. That means there is no other molecule which can fit here. And if you look at trans, it is more symmetrical. Symmetry will be symmetrical molecules will give a good arrangement in the crystal lattice structures. So we can say melting point order will be greater for trans than when compared to cis, because more void space is there in cis and less void space is there in trans. So that is why lesser the packing efficiency in the cis and more packing efficiency in trans. Not only this, we can also say that para molecules like X and Y, like dichloro systems, if you take, if I give these two molecules to you and ask a question like which has greater boiling point, like 1,4 dichlorobenzene, 1,3 dichlorobenzene, we have to say that 1,4 dichlorobenzene will be having a greater melting point. Okay. Why?
Transposition.
Melting point is greater in 1,4 dichlorobenzene. It is not cis and trans, no. 1,4, 1,3. Symmetry.
Because of voids.
Yes or no? Because of symmetry, the trans molecules, they are going to be like the 1,4 molecule is symmetrical in nature. Because of that symmetry, it will fit in the crystal lattice side greatly. Okay. Melting point order is 1,4 dichlorobenzene has higher melting point than 1,3 dichlorobenzene, and thus high symmetry, and 1,4 dichlorobenzene has higher melting point than 1,3 dichlorobenzene because of high symmetry and perfect crystal lattice structure. Perfect crystal lattice. Right. So whenever I am comparing melting point, I am looking at intermolecular, I am looking at packing efficiencies and symmetry. You may ask a question, sir, why are you not looking at intramolecular force of attractions? Why are you not considering the cis molecule and trans molecule? Why can't you compare the intermolecular force of attraction, and based on that, why can't you say it? Any idea why you are not comparing intermolecular forces when you are looking at melting points, whereas you are comparing intermolecular forces when you are comparing the boiling points? Because in the boiling point, to vaporize that particular liquid, the intermolecular forces are playing the dominant role. But here, when I am comparing melting point, already the molecules on the solid state. Solid state means already they have strongest intermolecular forces. The solids will have greatest intermolecular force of attractions. The intermolecular force of attractions are not differing greatly. The packing efficiency differs greatly. That is a dominating factor. Understood now?
Yes.
I'm not saying about cis and trans intermolecular forces when I am talking about melting point. Why? Because they are already in the solid state. In the solid state, intermolecular force are already strong. So the only dominating factor or differing factor is packing
Packing
efficiencies.
efficiency.
Right. Very good. So boiling point, cis molecule has generally more boiling point than trans molecule. Generally means in case the two types of groups are same. So mu net in the presence of cis is greater when compared to trans. So that is why you will be having more boiling point for cis when compared to trans. All of you write down this formula. Number of geometrical isomers. If it is an unsymmetrical molecule, number of geometrical isomers is 2 power n. Symmetrical molecule means number of geometrical isomers is 2 power n minus 1 plus 2 power p minus 1. 2 power n minus 1 plus 2 power p minus 1. Write down this formula, students, all of you. Unsymmetrical molecule, symmetrical molecule. So I'll give you the example to you. Try to figure out. CH3, CH double bond CH, CH double bond CH, CH double bond CH PH. Find out the number of geometrical isomers. How many students in all the three examples? Number of geometrical isomers. pH, CH3, CH double bond, CH, CH double bond, CH, CH double bond, CH, pH. In that case, is the molecule symmetrical molecule or unsymmetrical molecule?
Unsymmetrical.
Like one side we have metal,
Unsymmetrical.
other side pH. So unsymmetrical molecule. Unsymmetrical molecule means number of geometrical isomers is 2 power n. What is n? N is the number of restricted rotating system about which geometrical isomer is possible. N is number of restricted rotatory systems. Rotatory system about which geometrical isomerism is possible. So how many restricted rotation is there? Here we have only double bond system, that is restricted rotatory. So 1, 2, 3.
3.
Whenever you only have double bonds, N is nothing but number of double bonds in these cases. So how many are there? 3 double bonds. So 2 power 3, that will be 8. 8 geometrical isomers are there for the first molecule. Second molecule, symmetrical or unsymmetrical?
Symmetrical.
Symmetrical.
Symmetrical molecule, and how many double bonds are there? Like even or
4.
odd?
4.
1, 2, 3, 4. Even number of double bonds. Even number of double bonds is what the formula? 2 power n minus 1 plus 2 power p minus 1. What is p? P is equals to n by 2 when number of double bonds are even. So p is nothing but 4 by 2 minus 1. So 2 power 4 minus 1 plus 2 power 4 by 2, that is 2. 2 power 2 minus 1, how much it is? 2
12.
power 3. 2 power 3 plus 2 power 1. That is nothing but 10. Yes or no? Here in the last
Yes.
case, symmetrical molecule, Cl, CH double bond, CH double bond, CH double bond, Cl. Symmetry is there. So 2 power n minus 1 plus 2 power p minus 1. What is p? P is nothing but
N by 2.
n plus 1 by 2.
N
N is
plus
nothing
1.
but, so 2 power 3 minus 1 plus 2 power n plus 1. N plus 1 is 3 plus 1, 4 by 2. 4 by 2 minus 1. 2 power 2 plus 2 power 1. How much is that? 6. Okay. So this is the molecule. These are the cases. So these are the formula which you have to use. These formula are there to figure out the total number of geometrical isomers. For structural isomers, we have done the calculations, like how many structural isomers are there. If it is this type of structural formula, we have done all that calculation. Geometrical isomers, you can use this formula and do the calculations, right? Can you do the first one? This case. How many of you can do the first one?
Four.
4. Any other options? Any other option? How many double bonds are there? 2 double bonds are there. Symmetrical or unsymmetrical?
Unsymmetrical.
Unsymmetrical 2 double bonds means we have to use the formula 2 power
Per N.
2 power n.
2 power n. That will be 2 power how much? 2 power 2. That will be 4. Try to do it here, this example. Unsymmetrical or symmetrical? pH is there here. Unsymmetrical or symmetrical?
Unsymmetrical.
Unsymmetrical. Apply the formula now. Apply the formula and do the calculation. Okay. I think you can take these 2 examples as homework. Second and third example, you take this as homework. Apply the same formula 2 power n, 2 power n minus 1 plus 2 power p minus 1. P is equal to n by 2 if we have even number of restricted rotary system. P is equals to n plus 1 by 2 if it have odd number of restricted rotary system. And in the second example, you have to include this system also. That is the only point. This is also restricted rotating system. Third example also, you have to include that cyclohexane ring. Stereoisomerism. The first part of stereoisomerism is like configurational isomerism and conformational isomerism. In the configurational, we have discussed about geometrical isomerism, which is mainly due to restricted rotation around carbon-carbon double bond or cycloalkanes, around carbon-carbon single bond in cycloalkanes. So then the conformational isomerism is erased. Conformational isomerism is due to free rotation around carbon-carbon single bond. Conformational isomerism will be is due to free rotation around carbon-carbon single bond. Look at this molecule now. CH3 single bond CH3. In this molecule, carbon-carbon single bond, around that carbon-carbon single bond, as I have told you earlier, the one carbon atom can be rotating freely with respect to the other carbon atom, and there is no restricted rotation because in the process of rotating of one carbon atom with respect to other, there was no disturbance or breaking in the bond required. Okay. The different orientation of atoms or groups in space that results due to rotation around a single bond are called as conformations. And this phenomena is said to be conformational isomerism. This phenomena is said to be conformational isomerism. How many are there? How many number of conformational isomers are possible? How many number of conformational isomers are possible? Like how many number of structural isomers we can think of? Cis-trans isomerism we can think of. How many number of conformational isomers possible, students?
Infinite.
Infinite, because infinite angles are there. Yes or no? Infinite number of angles can be possible. So we can have infinite number of conformational isomerism. No one is going to ask about you the number of isomers because as they are already infinite. So they cannot be isolated at room temperature from each other as they are interconvertible at room temperature. One molecule and the other molecule, they are interconvertible because rotation is happening continuously. Bond length, bond angle are same in all conformers. So we look at this rotation is happening, because of that rotation, all the molecules are same. Different formula like projection formula to represent conformational isomers. Newman projection and Sauer's projection. Two projections are there to actually represent the conformational isomers or conformers. Newman projection, it is a front view projection of 3D molecule and a side view projection is Sauer's. Front view projection of 3D molecule is known as Newman projection formula, and the formula goes like this. Front carbon is represented by a dot and the back carbon is represented by a circle. Like if you look at this particular, I am saying this is carbon, CH3 bond, CH3 and single bond. Now this is your carbon, this is your carbon. Now I am looking at this molecule from the front direction like this. Okay. For me, this particular carbon is visible. For me, the back carbon is not visible. The front carbon which is visible to me, that is a dot. The back carbon which is not visible to me, that has represented by a circumference of a circle which you can draw. To the front carbon is only visible to me. Back carbon is not visible. In the front carbon, whatever the three groups are there, they are visible to me. Yes or no? If I am looking at the molecule like this, like my eyesight is looking at this atom. To this atom, we have three groups connected. What are those three groups connected to the front carbon? Those are hydrogens. Those are three hydrogen atoms. What about back carbon? Back carbon is, this is a front carbon. I am standing here and I am looking at the molecule in this direction. The three hydrogens on the front carbon are visible. Whatever the back carbon, are they visible to me or not visible to me?
Not visible.
Not visible.
You cannot say not visible because they are under continuous change in positions. Yes or no? This is front carbon, this is back carbon. The back carbon also has hydrogen. On the front carbon, I have a hydrogen like this. On the back carbon, also have a hydrogen like this. The front carbon hydrogen and the back carbon hydrogen, whenever they are exactly eclipsed, then in that direction I cannot see. But as the back carbon is rotating with respect to front carbon. You cannot say only back carbon is rotating, like one carbon is rotating with respect to other. We can keep one carbon fixed and I can rotate the other. So if I say back carbon has a hydrogen here, back carbon has a hydrogen here, back carbon has a hydrogen here, the rotation of back carbon can be done. If I can rotate the back carbon atom, the front carbon atom CH bonds are same, back carbon can be rotated, so the CH bonds can be visible again. Are you getting this logic or not?
Yes.
Yes, sir.
I'll ask a question. So this is a front carbon, CH bond is there. On the back carbon also CH bond is there. I can rotate the back carbon with respect to front carbon. What about the CH bond? This CH bond and the CH bond, what is the angle here?
120. 120 degree.
120
That-
degree.
Dihedral angle we are talking about, that was 120 degree. You may ask it out, sir, how come that angle be 120? Because it's a CH bond and it is a tetrahedral molecule, so it should be close to 109 degree, right? So this is a projection, okay? Projection formula. In reality, if you speak logically, that should be 109 degree or not? The CH bond angle, CHH.
Yes, sir.
Yes.
Yes,
So,
sir.
but this is the dihedral angle. This is not the exactly bond angle. Dihedral angle is what? Dihedral angle means angle between two planes. Dihedral angle means angle between two planes. That means this CH bond and the other CH bond, the front carbon and this hydrogen, back carbon and this hydrogen, that we are counting down. To the front carbon, one hydrogen is like this. To the back carbon also one hydrogen is like this. This CH bond will be in this plane. Like we can have a plane like this. We can have a plane like this. Yes or no? One more plane will be like this. Between two planes, there is an angle or not? The angle between the two planes, that is nothing but your dihedral angle. So this is one plane, CH bond plane, back carbons. This is a front carbon CH bond plane. So if I can rotate this paper with respect to other paper, I can change the angle. This is the angle between these two papers.
Yes, sir.
Yes,
So
sir.
that angle is actually changing, not the angle, not the CH bond angle. That dihedral angle is actually changing. So whenever you try to change this particular angle, we are saying the free rotation is possible around carbon-carbon single bond. Now just try to imagine the scenario. What is the dihedral angle, students? Dihedral angle was 120 degree. 120 degree. In the eclipse position, we have more repulsions or not? The hydrogen atoms, although they are not on the same carbon, this hydrogen and this hydrogen eclipse means they are in the close distance. So I'm looking at the molecule like this. This is hydrogen available like this. One more hydrogen is available in this fashion. This hydrogen atom overlapped. That is on the eclipse position. So they are at closer distance. So they will be having more repulsion. If I try to rotate the back carbon, I am going to have one more CH bond like this. If I try to rotate the back carbon, this back carbon can be rotated by an angle theta is equal to 0 to 60 degree.
60.
In the angle of 0 to 60 degree, it is moving away from this hydrogen or not? Up to this rotation.
Yes, sir.
Up to this rotation, the front CH bond and the back CH bond, the distance is increasing. But if you try to rotate again by 60 degree, what happens? Again, it is going through eclipsed conformation or not?
Yes, sir.
That means up to 0 to 60 degree, whatever the rotation is happening, that is moving in the direction of decreasing potential energy or not? Because repulsions are decreased. In the eclipse, more repulsion is there. Because of more repulsion, high potential energy. High potential energy. Rotation up to 60 degree. Okay, 60 degree. So potential energy decreased. Potential energy of the system is decreased. From the 60 degree, again, if you try to rotate one more 60, that is, if you go with 120, from the initial, it is nothing but 120 degree rotation. Again, repulsions are increased. So from 0 to 60 degree rotation, the potential energy is actually decreasing. From 60 degree to 120 degree rotation, the potential energy is increasing or decreasing?
Increasing.
Potential energy is
Increasing.
increasing means system is moving in a direction of stability or in the opposite direction of stability?
Opposite direction stable.
Opposite. And what is
direction.
our statement? Rotation is free about carbon-carbon bonds. How it can be free if it is moving in a opposite to the stability? So although we say rotation is free, rotation is free, rotation is not completely free. There is some strain whenever the carbon-carbon systems are rotation. Are you getting this logic or not?
Yes, sir.
Yes.
Although we
Yes,
say
sir.
carbon-carbon single bonds are free to rotate, but in the process of rotation from 0 to 60 degree, the potential energy is decreasing. From 60 to 120, potential energy is increasing. So there was a strain, that is van der Waals strain or torsional strain. There are different types of strains. Because of that strain, what happens? The rotation is not freely done. If the rotation is not freely, but still the rotation occurs. You may ask a question, sir, why? If it is moving in the opposite direction of stability, then why the rotation should happen? Why can't the molecule be in the 60-degree dihedral position? Because that repulsion is also it is there, it is less when compared to the actual molecular motions. Molecular motions are very high when compared to the repulsions. That is why the molecular motion or rotation will occur. Understood now? So back carbon. So front carbon and back carbon, front carbon and back carbon, not visible or visible? Front carbon is visible to you, back carbon is not visible. Sixty rotation, if you do, you will get here you have eclipsed form. Whenever you have groups at maximum separation, it is said to be staggered form. Eclipsed and staggered. Sawhorse position means if you look at the same molecule, I am looking at the molecule like this, you keep the molecule in this fashion. Earlier what I am doing, this is a carbon-carbon single bond, I am looking at the molecule in this fashion. Now what I am doing is I am keeping the molecule here only, just I am changing my position. Yes or no? I am looking the same carbon-carbon molecule, I am looking the same carbon-carbon bond by a side view. Side view projection of carbon, side view projection of 3D molecule, that is actually giving the Sawhorse projection. The side view projection of 3D molecule, that gives the Sawhorse projection. So this is nothing but Newman or not. If you look from this side, it is Newman only. If you look from this side, if I am standing here, it becomes Sawhorse. If I am looking at the molecule from the side position, it is Sawhorse. If I am looking at the molecule from the front position or along the carbon-carbon bond, that is Newman. Right? And Sawhorse position and Newman position, they can be again in the eclipsed and staggered forms. They are interconvertible because of free rotation around carbon-carbon single bonds.
Carbon, carbon.
Right, very good. So these are all the animations. Types of strains. What types of strains are there? Van der Waals strain and a torsional strain. What is van der Waals strain? When two non-bonded atoms or groups are brought close to each other, they repel each other. This type of repulsion is van der Waals strain or steric repulsions. Okay, so whenever you have two non-bonded atoms, like this is A atom which is connected to carbon, this is another A atom which is connected to carbon. These two atoms are close. Here in A atom we have electrons, here in A atom also electrons. Because of that we have repulsion, because those atoms are close. So minimum is in a staggered form and maximum in eclipsed form. Torsional strain, repulsion between bond pairs of electrons. If you look at bond pair, not only the atoms in A, like electrons in A atom, but also we have bond pair, right? We have carbon A bond, in that we have pair of electrons. Here also we have pair of electrons. They are also going to repel. That repulsion, when you try to take into account, that is torsional strain. Repulsion between bond pairs of electrons, that is the torsional strain. Repulsion between non-bonded atoms or groups, that is said to be van der Waals strain. Van der Waals strain will be maximum in the eclipsed form, minimum in the staggered form. And if you look at eclipsed form, again maximum in eclipsed form, which strain? Torsional strain, and almost zero in the staggered form. In the staggered form, the atoms are going to be separate out and the torsional strain would be almost zero. Okay, everyone got it or not? What they are trying to say is we have a CH bond here, carbon hydrogen bond is present here. This hydrogen atom, this CH bond, this CH bond, this hydrogen atom, they can repel. Or if you have CH3 group here, CH3 group here, the two methyl groups can repel. And we also have carbon-carbon single bond. In that carbon-carbon single bond, we have bond pair of electrons. They can also repel. If the repulsion is between the two groups, that is said to be van der Waals repulsion. If the repulsion is between the bond pair of electrons, that is said to be torsional strain. So torsional strain and van der Waals strain, they are maximum in eclipsed forms. In staggered form, the torsional strain is almost zero and it is minimum in the staggered form. So van der Waals strain, eclipsed form more strain, staggered form will be having less strain. Dihedral angle, angle between two bonds of adjacent atoms. Two bonds of adjacent atom means it is nothing but a angle between two planes you will get. In ethane, angle between the front carbon and hydrogen bonds, like this front carbon and hydrogen CH bond, back carbon hydrogen. Back carbon hydrogen bond in the Newman projection, that is nothing but your dihedral angle. So in the eclipse, dihedral angle is theta is equal to 0. If you try to rotate by 60 degree, you will get staggered form. Theta is equal to 60 degrees. If you try to rotate further, stability order, which is going to be more stable, eclipse or staggered? Staggered will be more stable when compared to eclipse. Why? Why means you will be having less repulsions.
Less.
In ethane, staggered form is more stable than eclipse form by 12.5 kilojoule per mole. This much energy is the difference between eclipse and staggered form due to the repulsions. Yes or no? And this much energy, if you try to provide, then both are interconvertible directly. The molecular motion is obviously greater than this much energy. That is why staggered and eclipse form, they are continuously interconvertible. Conformations of ethane are infinite. Okay, infinite number of angles are possible. Infinite number of angles are possible. Try to look at this molecule CH3 ethane, and if you try to look at this molecule, like in the Swartz position means you are looking at the same molecule in the side direction. If it is Newman position, you will look at the same molecule in the along the carbon-carbon bond. Eclipse theta is equal to 0. In the staggered, you have theta is equal to 60. Further, you can rotate by 60 more degree. If you try to rotate 60 more degree, you will get what? You will get again eclipsed or not?
Eclipsed.
Again, you will be getting eclipsed. If you try to rotate by 60 more, again try to rotate. Any other intermediate in between staggered and any other intermediate, whatever you are going to have, that is nothing but skew conformation. Any other intermediate is nothing but skew conformation. So stability is nothing but staggered will be greater when compared to skew. Skew will be greater when compared to eclipsed. Eclipsed means theta is equal to 60 degree. Theta is equal to 0 degree. Staggered means theta is equal to 60 degree. Skew means any other form, any other angle. So when compared to 60 degree, the any other angle will have more repulsions and less stability, and when compared to 0 degree, any other angle will have less repulsions, obviously more stability. Right? Potential energy diagram, if you try to look at, if you take the potential energy in the y-axis and degrees of rotation or dihedral angle in the x direction, at 0 degrees, if that 0 degrees is the dihedral angle, potential energy is maximum. Potential energy is going to maximum. At 60 degrees, potential energy is minimum. Potential energy is minimum. At 120 degree, again potential energy is going to be maximum. At 180 degree, again potential energy is going to be minimum. 240, again maximum.
Maximum.
300, again minimum.
Minimum.
360, again maximum. So
Maximum.
this is how the potential energy is going to be changing for the respective molecule of ethane. Conformations of ethane in the potential energy diagram. Conformations of ethane and potential energy versus dihedral angle plot. Everyone understood these points or not?
Yes.
Yes.
Yes, right. So this is the potential energy where the maximum potential energy we are seeing This is a state, energy state where the minimum potential energy is seeing. So conformations of ethane and potential energy versus dihedral angle plot, that will be in this fashion. And the difference between this energy is 12.5 kilojoule per mole, as we have mentioned earlier, and it was the value given experimentally, which has been observed in reality. And now the interesting scenario is we can actually have the conformations of N-butane around C2C3 carbon also or not. All of you understand this point carefully, students. Around the C2C3 carbon also we can have a conformations of ethane. If you observe that carefully, around the C2C3 carbon also we can have the conformations of ethane or not.
Yes.
So now we will understand about this particular conformers in reality, like how the different conformers are there and how we can actually understand their energy changes and what are those molecules called as. All that points we are going to look at now. So in this scenario, we have two cases like gauge form, anti-form, all those also coming into picture. What are gauge forms? Anyone knew about gauge forms and anti-forms? Yes or no? Anyone knew about it? We'll draw all those molecules where we have gauge forms and anti-forms, so that you can understand how actually, if you try to draw for ethane, it's simplest case because the side atoms are going to be same. If you try to draw that for a molecule like butane around C3 C2 carbons, then you will be getting the complete idea. Now we'll take the molecules. Yes or no? Now around this carbon C2 C3, this is my front carbon, this is my back. So I am having this particular molecule front carbon. To the front carbon I have methyl group connected and two other hydrogens connected. On the back carbon I have CH2 CH3 methyl connected and two other hydrogens connected.
Hydrogen.
This is nothing but fully eclipsed form or not? This is
Yes,
eclipsed
sir.
form obviously, and we are saying fully eclipsed. Why? Because the two bulky groups, that is
Methyl
methyl
group
groups, they
on
are
same
having
side.
more repulsions. 60 degree if you try to rotate, you will get what conformation? The front carbon I am keeping same, the back carbon I am rotating CH3HH. Again try to
60
rotate
degree.
60 degree. CH3H CH3HH, and here you have CH3, here you have hydrogen, here you have hydrogen. Rotate by 60 more degree. CH3H
Methyl.
methyl will be here. Two hydrogens are in this direction. Again rotate by 60 more degree. CH3HH, CH3 will be present here. Hydrogen will be present in other two fanus. Hydrogen, hydrogen. Again try to rotate 60 more degree. CH3HH. We have CH3, hydrogen, hydrogen. If you try to rotate again 60 more degree, you will get fully eclipsed. Yes or no? So what is this? It is fully eclipsed. What is the second confirmation? Partially.
Gauge form.
Yeah, partially staggered. I can write this as partially staggered, which is nothing but gauge form. Partially staggered is nothing but gauge form. And the third form is partially eclipsed or not?
Partially eclipsed.
Partially eclipsed. And the fourth one is
Anti.
fully staggered.
Fully staggered.
Fully staggered is also called as anti or anti. And the next one, it is nothing but partially eclipsed.
Partially eclipsed.
Partially eclipsed. And the next one is going to be
Partially
partially
staggered.
staggered, which is nothing but gauge form again. So what is the order of stability? Stability order, try to give. Stability order, can I say anti is going to be more stable because of least repulsions? Anti form.
And
After antiform, generally we'll have Gauge
Antiform.
form more stable. Yes or no? After Gauge form, you'll have partially eclipsed.
Eclipsed.
partially
We have
eclipsed,
fully eclipsed.
fully eclipsed.
And this order is going to be changing whenever there is intramolecular hydrogen bonding. Remember, this is not 100% valid. Whenever the intramolecular hydrogen bonding is possible between the groups present on second carbon and fourth carbon, in that case, the stability order changes. This is the case when there is no, this is the case when there is no intramolecular hydrogen bonding between, when there is no intramolecular hydrogen bonding between groups in C2 and C3 carbons. When there is no intramolecular hydrogen bonding between groups in C2 and C2 carbon, then only this will be stable based on the repulsions. If not, the order is going to be changed. Right? So let us look at all the conformation now. So this is nothing but your eclipsed. Then you have, if you try to rotate, you will have
Gauge.
partially eclipsed, partially staggered,
Partially staggered,
partially eclipsed, anti,
partially eclipsed, fully
then again
staggered.
partially eclipsed. So like that, you will be getting all the conformations. Fully eclipsed, gauge, partially eclipsed, and anti.
And
If you try to look at the angles 0, 60, 120, 180 degree, and look at the stability order. If you compare the stability order, gauge form is when dihedral angle between two bulky groups is 60 degrees. Stability order, what is the order of stability, students? Order of stability will be anti greater than gauge.
anti-gauge,
Partial
partial
eclipse,
eclipsed,
fully
and fully
eclipse.
eclipsed.
Yes, very good. This is a stability order. The same thing, whatever we have explained, that is in the slide now. Anti-form is when the dihedral angle between bulky groups 180. Gauge form is when the dihedral angle between bulky groups 60. Skew form means there are infinite conformations, right? Between eclipsed and staggered forms, there are whatever the forms are present, they are said to be skew forms. Whatever the conformations we have, they are said to be skew forms. And you can write down gauge form is more stable. Gauge form is most stable when there is intramolecular hydrogen bonding. Okay, intramolecular hydrogen bonding. It is not necessary that anti-conformation is always more stable than gauge conformation. Due to intramolecular hydrogen bonding or electrostatic force of attraction, gauge form becomes more stable than anti-form. This is what I am talking about. Like whenever we have CH2OH and CH2Z, Z can be fluorine, COH, NH2OH, NO2, CH3. So look at the number of molecules, very high number are there. In all these cases, what is going to happen? Due to intramolecular hydrogen bonding, the stability of gauge form is extremely high. So like this case, we can consider the molecule like this, CH2OH, CH2F. What is this called as? 2-fluoroethanol. 2-fluoroethanol. If you consider 2-fluoroethanol, which conformant is more stable? In 2-fluoroethanol, the gauge conformant is the most stable. Why? Due to intramolecular hydrogen bonding. But no one is getting any doubt. Sir, you should ask a doubt like, sir, why you are saying intramolecular hydrogen bonding is present or more in gauge form? Why can't you take the fully eclipsed then? In the fully eclipsed also we have intramolecular hydrogen bonding, right? OH is there, fluorine is here. Even the groups are nearer. So partial positively charged hydrogen, partial negatively charged fluorine, they should have even more attraction. Yes or no?
The repulsion will be greater.
The repulsion will be greater. That is simple logic. The repulsions are higher in fully eclipsed form. Even though we have intramolecular hydrogen bonding, the repulsions are dominating. Due to that, this intramolecular hydrogen bonding is stabilized only in gauge form. Intramolecular hydrogen bonding is not stabilized in fully eclipsed due to more repulsions. Okay.
Yes.
Special cases, ethylene glycol, CH2H, 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 CH2H. So look at that. So in this, Gauge form is more stable when compared to anti-form. Gauge form has intramolecular hydrogen bonding. Anti-form do not have intramolecular hydrogen bonding. So ethylene glycol, if you consider the case, in ethylene glycol, Gauge form is stable when compared to anti-form. Next, draw most stable conformer of this molecule: CH3, CHOH, CHOH, CH3. What is molecule? Butane 2,3 diol.
Diol.
Yes.
2, 3, diol.
You can have this case. Like you have two OH groups in this fashion, two methyls away. Intermolecular hydrogen bonding is there. This is going to be the most stable form. But you can also have another possibility. You can also write this in this fashion: OH group here, OH group here, CH3 here, hydrogen here, CH3 here, hydrogen here. Here also we have intermolecular hydrogen bonding. Okay, but repulsions are high. The CH3 groups, wherever there is no intramolecular hydrogen bonding possible, those bulky groups you separate maximum, and those groups where the intramolecular hydrogen bonding is possible, you keep those groups at the gauge. Then you say that molecule is the most stable conformer. The molecule where the two OH groups are at an angle of 60 degree and the two methyls are maximum separated, that will be the stable molecule. This is the correct gauge form which is more stable. Draw the most stable conformer of this molecule. In this molecule, the most stable conformer is what? To the front carbon, this is the carbon to which I am weaving. So this carbon I have methyl and COO minus. To the other carbon I have methyl and H. Methyls are not having any intramolecular hydrogen bonding, so I'll separate them maximum. And to this particular carbon I have hydrogen. Yes or no? Hydrogen and C double bond O minus. C double bond O minus is there and one hydrogen. And the other carbon I have NH4, NH3 plus. Methyl have separated hydrogen. So now they have intramolecular hydrogen bonding. So this is the most stable. Okay, the groups which show intramolecular hydrogen bonding I have kept at gauge. The groups which are bulky I have placed in the anti, and that molecule I have drawn, that is nothing but your most stable Newman projection. Got it or not?
Yes.
Both the molecules are same. Just in this molecule I have written COO minus in the front carbon. Like I am looking the molecule in this fashion. In the molecule which they have drawn, they are looking at the molecule in this fashion. Both are same only. If I am observer is looking from this, this is the front carbon. If observer from looking from this is the front carbon. The change, the direction in which you are looking at the molecule, that is actually changing the groups in the Newman projection. Like I am saying this because if you have doubt any NH3 plus is above, CO minus is below means both are same, not an issue. Right? Then you have conformational isomers of cyclohexane. In the cyclohexane also different conformers are possible. Cyclohexane exists in 4 forms. What are those? Chair form, boat form, half boat, and twister.
Twisted boat.
Twisted boats. Out of all those, chair form is actually going to be more stable. So you can have the conformers like this. Yeah, these are the conformers. With this diagrams, you can have a clear idea. Chair form is in this fashion, boat form is in this fashion. Like you can look at twisted boat form and half chair form. Twisted boat means you have just twisted the boat and half chair will be in this fashion. Chair form is most stable conformation of cyclohexane. For cyclohexane, chair form is more stable. Stability order is chair will be stable, then twist boat, then half chair. But in reality, if you go into the higher standard like MSc, twist boat will also have more stability. But as of 12th standard, this is the order you have to follow. No confusion with that. Twist boat, that will also have more stability if you go with different sets of molecules. So there we have done a lot of research, no? So there, if you go with the different sets of molecules, twisted molecules are they are also going to have more stability because of minimum repulsions. As of 12th standard, this is the order you have to follow: chair, twist boat, boat, half chair. Chair form will be the ultimate stable, then twist boat, then half chair. This is order. This stability order is given based on the stability order. The order of stability. The order of stability is given based on repulsions. Based on repulsions. And if you try to write again, like few more concepts, if you want to understand from this chair form and boat form and twist boat and all these formats, we can understand that. By drawing the formats. So if you try to look at the chair form, students, chair form will have this type of configuration. Yes or no?
Yes, sir.
Exactly understanding means this will be the position. So these three hydrogens, if I give numbering 1, 2, 3, 4, 5, 6. On the first hydrogen, we can have axial and equatorial. The hydrogens you can name as axial hydrogens and equatorial hydrogens. What are axial?
Perpendicular.
Which are perpendicular? Like the hydrogen HA you can write, HE you can write. On the second position, I can write HA like this, HE like this. On the third position, I can write HA above, HE down. Like first, second, third, fourth, if you go, fourth, again H axial down, H equatorial above. Fifth, H axial above, H equatorial below. Sixth and fourth, they are going to matching. H axial below, H equatorial above. Now look at the positions. 1, 3, 5. They are all above. These are carbons present. Carbons present above. And in these carbons, axial carbons are above. Axial carbons are up. And equatorial are down. And equatorial. Axial hydrogen we are writing, right? These are axial hydrogens. 1, 3 and 5, they are up actually, and axial hydrogens are up. This is up, this is up, this is also up, and equatorial hydrogens are down. 2, 4, 6. These carbons are carbons. These are carbons present below, and in these carbons, axial hydrogens are
Down.
and equatorial are
Up.
up. Right? You have to understand, if we have placed the positions on the first and third, okay, the first and third carbons will experience 1, 3 diaxial repulsions, and the hydrogens are called as, and these hydrogens are called flagpole hydrogens. Whatever the hydrogens we have on the third position, third carbon atom and the first carbon, they are going to experience more repulsion. This is nothing but repulsion. Because of that repulsions, whatever the bulky groups we have, we should not place them on the first and third axial positions. Is that clear or not?
Yes, sir.
Yes, sir.
Okay. And whenever you have, what is this configuration? Cis configuration means same side the groups are has to be present. If you have 1-2 systems, like if I have the substitution like this substitution, okay, 1,2 or di-substituted cyclohexane will show cis-trans isomerism. Like if you have configuration like this, I have methyl here, let us say, and on the second also methyl here. So if I have 1-2 substitution, cis means what? Cis means what, students? Cis means same side should be present. Same side should be groups present. Groups should be on same side. Group should be on same side means the methyl CH3 has to be axial. One methyl is going to be axial and the other methyl is going to be equatorial.
Equatorial.
Yes or no? Because if this is axial is up here. Here the other hydrogen is up here. So this is nothing but cis or trans. Group should be on same side means axial equatorial.
Sure.
This will be true. Axial equatorial or equatorial axial. Trans means
Axial and
Axial,
equatorial,
Axial,
equatorial.
or
axial,
equatorial,
equatorial.
like that we can write for 1,3 also. For 1,3 cis means what? This is for 1,2.
Axial, equatorial.
Axial or equatorial. Trans means
Axial, equatorial, axial.
1,4.
Axial, equatorial, axial.
Equatorial axial. Trans means
Axial, equatorial.
axial or equatorial. So this is the extra concept which I have given. You don't worry with that part, okay? But you can just understand where the repulsions are going to be high. 1,3 diaxial repulsions are high. Wherever we have two bulky groups in the same axial positions, that is going to be unstable because of more repulsions. Right, students, this will be completing your conformational isomerism, geometrical isomerism, cis-trans and structural isomerism. We have two more things, that is optical activity and tautomerism. As I have told you, tautomerism will start in GOC only because we have to include the Betz rule. Next class we will discuss about optical isomerism and all the properties, right? And very happy Christmas for all of you. Thank you all.
You too, sir. Thank you.
Thank you, sir.
Thank you.
Thank you,
sir. Thank you, sir.